Please take note of the following. And thank you to our sponsors for this event. Hello everyone, welcome to this session. My name is Stefan Moret. The session is titled The Convergence of Machine Learning Operations and Actuarial Control. This content is from a paper written by Neil Pretorius and I. It's work that was sponsored by our employer. We're very thankful, and we've got amazing support from Dynamo Analytics. We supported this research. So we hope that learnings from this content could be applied in like our internal workflows, at least the way we build actuarial models and the way that we think about it, but also in the software platform that we build. So it's steered in an opinionated way according to more modern practices that's geared to and tailored to fit the needs of machine learning modeling as well in traditional actuarial spaces. And then just to give a bit of a signposting, just to do some signposting, I'm going to start by just giving a broad overview of our key findings. It's not going to make too much sense initially, I guess. And then I'm going to take a step back and do proper introductions of machine learning operations, doing a quick recap of what is the actuarial control cycle for those of us that can't remember from university, and then after these introductions of some of the key concepts, I'm going to hand over to Neil, who will be making things a bit more practical with a case study to flesh out and illustrate the concepts better, and then he's gonna take it further and then conclude and then repeat basically our key findings, and then hopefully they'll make a lot more sense. So that's just a bit of an idea of what's to come, and I really hope you enjoy the session. We're quite passionate about this work, as you can probably tell, enjoy. So at the time of introducing the actuarial control cycle for the first time to the actuarial profession in the UK, Jeremy Goffert, the president of the IFOA at the time, he wrote this. So in a world of transition for all our disciplines, actuaries can keep ahead of the changes by first getting our thinking right. And what's interesting is this was written in 2003, when there was obviously a lot of change, especially digital and technology changes happening. The way in which we build our systems, our workflows, like actuaries' workflows, were changing radically with the introduction of more modeling softwares and everyone getting a laptop, and just the whole workflow was changing. Paper-based systems getting digitized. All of a sudden, automation became possible. And today, arguably, we face even more changes with machine learning modeling, like radically changing the way we do modeling. There's generative AI that can just help our workflows, assist us. We can do robotic process automation. There are process industrialization happening. Not just the paper-based processes that were digitized. It's not just paper-based processes being digitized. It's now that those digitized processes are now being reimagined, and so that that's my view of process transformation projects. So there's a lot happening today, and the key research question of this topic was actually, do we today have our thinking right, and is the actuarial control cycle still useful? And And our conclusion is, yes, it is still useful. But we must note that machine learning is augmenting traditional actuarial models. There are challenges in just generally deploying and building machine learning models by machine learning engineers. And there are two cycles, one from the machine learning operations, MLOps, and the Actuarial Control Cycle, but they have the same goal. And finally, we conclude that machine learning ops principles that is a set of best practices in deploying and building machine learning systems. Adopting those principles will be very beneficial for actuaries, and it can even enhance the actuarial control cycle in the way we currently see it. So that's our key findings. So let's take a step back. Where did this all begin? I'm going to tell a story. The story is about a junior data scientist called Steve. Now, Steve is the first data scientist to be recruited by a small bank. And this bank, they're only like a newly established player, and they don't have a fraud detection system. So they asked him, Steve, can you build us a model which can detect when a transaction is fraudulent with as high accuracy as possible as you can? Okay, so now Steve is excited. He knows all the theory. He's confident. He's taking ownership of this massive task, I guess. And he works with various departments to get the data that he needs, and he cleans the data. He works through everything, and he downloads all the data on his laptop, and then he works through it, and he starts building a model. And at first, he starts building a rule-based model, and just trying a bunch of things, and then later on, Steve realized, but if he uses the given individual, like the bank account individual, if he uses that person's most recent transaction history, say the last 50 transactions, he can accurately model the behavior. So if the next transaction is out of place compared to the last 50 transactions, then he figures out that he can build a model which is really accurate. And Steve focuses on this model, and the model is the main thing. It's this massive, all he focuses on is building this model. And it just happens to be that he works mostly on his laptop, he gets to a point where he's trained a model that is super predictive. In almost all cases, like 99.9% of the time, it's successfully predicted fraud when he tests this on cross validation techniques. So out of sample data, when he looks at out of sample data, he's confident that this model is going to work. He's going to get promoted. He's excited about the management just seeing him, obviously, and he's going to make a name for himself. And then he's now psyched up, ready, walks over to the IT department, and now he wants to discuss getting this model deployed. And the first thing they tell him is, Steve, but you realize that we don't have the transaction history available at the time of transaction. There's no way we can get that. The latency and the runtime is just, it's too far away in databases. It's going to take much too long. It's going to wait way too long to get those 50 transactions. And then Steve goes back to square one, because really, this was all he was focusing on. And then over time, months pass after that, Steve realizes that the model is actually a really small and not so important part of the wider machine learning system or the infrastructure supporting the model. So one of the key fundamentals of machine learning operations, the MLOps, is that the supporting environment of the model is more important than the model itself. Okay, if we get our data verification, data collection, our automation, and if we have really good feature extraction processes and we have really good monitoring in place for the model, that is arguably 80% of the value. If we have really good supporting systems and infrastructure with a very, very basic model, in most cases that is a better performing system than a very predictive model with poor management tools or poor cloud infrastructure supporting the model. So this is a key point about MLOps. It's not about the model. So let's summarize this. What is MLOps? We know that the infrastructure is more important than the model. The supporting infrastructure is actually it's complex. It's something that should not be underestimated. And in developing machine learning systems, we've actually faced similar challenges to software engineers. So MLOps is the application of DevOps principles which aim to fix the challenges faced by software engineers, but applied to machine learning systems. So that's where the name comes from. MLOps, DevOps. Okay. So all the principles that typically apply to DevOps, test-driven development, continuous delivery, a focus on automation, automated like the CI/CD pipelines, automated testing, all those principles, if we apply them now to the machine learning system and modeling, then we end up with MLOps. Okay, so that should give you a bit of an understanding if you know DevOps. So MLOps is a opinionated way of applying that to modeling and the modeling system. So if you go and study MLOps, one of the resources you'll find is the Machine Learning Lifecycle. So it differs a little bit whether you get it from AWS resources or for example from Google. But our consolidated view of this is here on the screen. Okay, it starts by problem definition. So scoping is a really important part of building a machine learning system. Scoping should include the entire life cycle of the project. So you should consider all the steps right up to deployment when you scope. And then after scoping, it starts with the data process because we're building a system. The assumption is that we're building a system which is data driven. So after that, we've got modeling. And what's interesting here is there's an opinionated flow of how you select and train and select models. And after that, you analyze whether the model is fit for purpose, so error analysis. So some in the industry would also refer to that as model evaluation. So this refers to like scoring a model or having an automated approach of actually testing a model, one model versus another, and then in a more data-driven or empirical sense, picking which model performs best. And then after that, we've got deployment of the model. So this is where the model is practically incorporated, built into or built next to current software systems. So for example, like with the fraud detection case, so that's like a model deployed for real-time evaluation or real-time execution. So on a case-by-case basis, the model can predict fraud or something like that. So it's often in partnership with engineering teams. And then also what's really, really important is an automated system of maintaining and monitoring models. So that's finally considered. So this includes, automated monitoring of data drift or concept drift. So some ML concepts. But it comes down to like automated detection of trends. And like the initial scoping phase would also consider, how do we test for changes in real life, or how will we also be testing on a day-to-day basis whether the model is still performing well. So the machine learning lifecycle is cyclical. Okay, at any point in time you go back to the previous step. It's really seldom that you'll run through the entire it's really rare that it doesn't really happen that you would run through the entire process without going back to a previous step. So from problem definition to final deployment, this cycle is actually it's quite similar to the actuarial control cycle. So let's have a look at that. So just a quick recap. The actuarial control cycle starts with problem definition, develop the solution, monitor the results. Okay, this is typically applied in a context that is different to machine learning workflows and sort of different to an engineering context. It's often more, let's say we've got a business problem, we're going to develop a model of like not on a server, it's more like on a computer, or potentially even like a handwritten calculation in theory. And then once we're done with that exercise, we then typically write a report with the key findings, and then what made the actuarial control cycle so nice was it gave us a workflow for that process, so that with our previous actuarial investigation or our profit testing or reserving exercise, we now have a framework that we can use, that every time we need to run this problem, we need to continually monitor the results, monitor the previous report's results versus the current, updated model based on updated data. So it gave us a framework to work with in like a cyclical framework to actually work with our models. The key thing about the actuarial control cycle, which is then obviously a little bit different to the machine learning life cycle, is we don't explicitly consider deployment, but also everything must be governed by like we must always consider external forces, external trends happening, market trends, and everything is embedded in professionalism. So that's the key differences. With machine learning systems, it doesn't have that professionalism component. Arguably, anyone can call themselves a data scientist or a machine learning engineer. I think actuarial, if you have actuarial word in front of something, typically it's a bit more robust. The public knows that they can trust it. So that's something to be proud of, and something that actuaries get really well, and that they do well in. So okay. So now I'm going to hand over to Neil, who's going to do the rest of the presentation, and hopefully color in these concepts and hopefully give a lot more context to the introduction that I've done.
Good day, everybody. My name is Neil. I'm a colleague of Stefan, and over the last few months, I've had the privilege of writing this paper with him. I'm going to be taking us through a practical example of two teams setting out to solve a pricing challenge. The one team will be guided by the ACC, and the other team will be guided by the Machine Learning Lifecycle. So let's start at defining the problem. The team following the ACC will be focusing on strategic clarity. For them, it is most important to solve the challenge within the given parameters. On the MLL side, the team will be looking more at production readiness and integration. So they'll be taking a much more pragmatic view of the solution. When we collect data, the team under the ACC will be looking at periodic data, manual extractions. We're talking spreadsheets, in some more advanced cases, maybe some SQL extracts, and so forth. But the focus will be on periodic. It will be points in time. Whereas the team following the MLL will be looking at automated pipelines. We're talking transform or extract, transform, load, running on an automated schedule, and this is continuous. They'll be looking at getting the latest version of the data at any given point in time. Processing the data under the ACC, this will be semi-automated. We'll be working with static data sets, so we'll be doing our feature engineering, data cleaning, all those type of things on static data. Sometimes this will be semi-automated, but it won't be fully automated. Under the MLL, once again, we'll be looking at integrated pipelines similarly to our data pipelines that we built for extracting data and collecting the data. And another big focus here will be orchestration. At what points in time do we process data again? Feature engineering and EDA. Under the ACC, this is a manual process. We'll be focusing on inference and interpretation. Under the ACC, interpretation is probably one of our biggest goals. We want to be sure we can interpret our results and that we can always be able to answer questions from the regulator, whereas under the MLL, the focus once again will be pipelines. These pipelines will be used to build feature stores, so we'll always store our features. We can reuse them, we can change them, we can drop features, we can add features. Once again, very, very automated process. And under the MLL, something that I think is very important for governance in particular is here we already look at what metrics we're going to be using to evaluate our performance of our model, not just during training, but also over time to preempt changes in our population, changes in our model, when is our model not performant anymore. All of these will happen within the feature engineering step, whereas under the ACC, we will not really be paying much attention to this. Selecting the model, ACC governance is top of mind. We'll be looking for an interpretable, domain-driven model. So here you'll generally have people with deep domain expertise solving a pricing challenge. So here we're probably speaking about general insurance actuaries heavily involved in model selection, whereas under the MLL we'll be looking at the performance. Is our model predictive? Is it accurate? We'll use measures like the F1, precision, recall, those type of things. There won't be much consideration given to the domain, but we'll purely look at metrics that we have defined in the previous step. Training our model under the ACC, data-driven parameter estimation. It's a linear process, it's step by step, and there's some overrides as well, which will come from the domain knowledge. So here we will once again have a subject matter expert working with the model, and there might be some overrides, whereas under the MLL, we optimize for performance. We've got automated retraining. It's an iterative process. We'll train a model, look at our outcomes, retrain the model, once again in a very, very automated way. Evaluating our model under the ACC, it is once again very periodic. It's static validation, and we focus on compliance. We need to keep the regulators happy. We need to make sure that we treat our customers fairly, that there's no bias in our models. Whereas under the MLL, we use cross-validation. There's fairness audits. Very automated process, very continuous. Very, very little manual intervention. Maybe initially you'll have somebody that considers the model, looks at it, and evaluates it through human with a human in the loop, whereas going forward we will have very automated triggers at any given time should something change within our data. Once again, population changes, model degrading, testing for model drift, data drift, those type of things. Whereas under the ACC, it's very periodic. We'll have quarterly reviews, possibly monthly, but it's very unlikely. I would say from a frequency point of view, we'll probably be looking quarterly and in many cases even annually. Deployment, this is really where the machine learning lifecycle shines. We'll have deployment pipelines, we'll have very strong model version control, we'll have deployment strategies. This could be blue-green deployment, canary deployment, and there's various deployment strategies. And what this enables us to do is to continuously integrate, continuously deliver models that should we change and test, and we don't have to roll this out to our entire user base. We can control this through deployment strategies to make sure that we don't break anything. So this is very, very good for things like A/B testing as well. Whereas under the ACC, you've got a model with fitted parameters, it's handed off to the IT team, it's implemented, and it is monitored periodically, once again, quarterly, annually, in very, very seldom cases, monthly. I've touched on monitoring before. Let's quickly go a bit deeper into that. Under the MLL, this will happen in real time because we've built very, very rigid pipelines. This we can do drift detection here, that's more relating to model drift, but we can also monitor for data drift, and this really enables strong compliance. It's an automated process. Should something change, there can be an alert. Owner of the model can respond to that by either changing features, retraining a model, and then once again through deployment we can manage this pretty well. So yeah, this is really where the MLL shines. Under the actuarial control cycle, we'll have periodic reviews, monthly, quarterly, annually. There'll be regulatory reporting, and we'll do static trend analysis. Very, very manual processes, lots of human time in it, whereas under the MLL, very automated, making use of pipelines and alerts. So what did we learn from our practical case study? We had two teams, we had the same problem, and we used two different cycles to solve this problem. I think it's very clear that we've got two very distinct cycles, yet we've got one goal, with the biggest similarity being that both are iterative frameworks and both are used for solving problems. The MLL has got an explicit deployment step, which is really where it shines. What this enables us to do is have very strong governance around model versionings, and it also breaks down the silos between setting up a new model and getting it into production. The MLL also has automated monitoring. This removes a lot of time to insights because you don't need people to manually go and pull statistics to see how the model is performing, review our population of data to see if there's any changes or anything like this. This will be automated because we've built pipelines to do this. The MLL also considers infrastructure very early on. What this enables is that we don't have any surprises down the line. Should we invest a lot of time to build our model, we hand it over to the next team, and at that point they tell us, listen, our infrastructure can't support this model. Then you're back to square one. Whereas under the MLL, we would have picked this up very early on, and we would have probably considered a different model, or just the way we set up our model could have been different. So this is also a very important step under the MLL. The MLL has got near real-time feedback. What this enables us to do is to pick up if there's been data drift, model drift, concept drift, any of these. We'll pick it up early and we can react. Under the ACC, this will most probably only be picked up either at year-end review or if there's quarterly reviews. So that makes us react much slower. Whereas under the MLL, we'll get this information quite quickly, we can react, and this can save us a lot of trouble at that point in time. So what did we learn from our practical case study? We could clearly see that deployment is the missing link. So why does deployment matter? Well, firstly, it forces us to have rigorous data engineering. Data engineering, in my mind, is like a cheerleader. I know it's a very, very weird analogy, but for those of you that watched Heroes in the mid-2000s will remember the phrase, save the cheerleader, save the world. So to my mind, data engineering is the cheerleader. Get this right and you'll have a good model. Secondly, it enables governance. Governance is as important as a good model. If you can measure it, you can manage it. Lastly, continuous monitoring. What this enables is you don't have to have periodic reviews, which removes a lot of time spent by teams. And secondly, it enables us to react timeously. We don't have to wait for a quarterly or annual review to notice that something's wrong. We can react to it as soon as it happens. So, where does this leave us? Reimagine the ACC with the explicit deployment step. Let's conclude. Actuarial models are changing. Big question, should our frameworks too? It is clear to see that ML is augmenting traditional actuarial models. Challenges integrating these ML models into operations is plaguing us all. The ACC and the MLL are two cycles, but they've got one goal. From what we've discussed, we can clearly see that MLOps principles can enhance the ACC through an explicit deployment step. Thank you so much for taking the time to listen to Stefan and myself. There's a live Q&A in the chat. Please ask questions there. Let's have some good discussions. There's a link to our paper. And also, please connect. It would be great to follow you guys and see what you're up to. Once again, thank you so much for your time.